All right, so for today, I want to, everybody can hear me okay, first of all? Give me a thumbs up, good. I want to get into a little bit of calculus, but there are just a few items of business that we got to attend to first. So let's take a look here. Online assignments. So for now, we are going to be using Math Excel. Typically, I do some Moodle for my calculus class as well. This year, for some reason, the district has decided for the first year not to host Moodle, to support Moodle, and so we're scrambling to try to find a place to put my Moodle. But when we do, we'll use a little bit of that also. We'll create accounts, and I'm assuming we'll at some point have access to that again. But most of it will probably be done on Math Excel. That's not, we don't have the accounts set up yet for you guys. It should be very shortly. As soon as it is, we'll take care of that item of business. But for now, we're going to have just probably a couple days where we're going to be using Canvas for you guys. And I don't know how much Canvas we're going to use, but it might be something we rely on. I'm able to use some of my Moodle questions in Canvas. It's just not quite as good of an environment. We'll talk about that here in a little bit, about how you're able to get into Canvas and do those assignments. So don't let me forget. We'll come back to that. Notebooks. You already know the drill on this from having me a couple years ago. I know that we're remote learning here, but it's really important that you get yourself a notebook so that you can organize the work that you're doing on these assignments. During our office hours that we'll talk about here in a little bit, the easiest and best way for you to get help from me is for you to have a notebook that you can just take screenshots of, and I can see what's going on. I can give you some assistance as to where you're headed off track. So just like before, I think the best notebook that you could get would be maybe a spiral one with some graph paper in it. Enough said. If you have questions on that, let me know. Attendance. I get that it's pretty easy. I'm going to make high quality videos for everything that we do. If you do miss class, you can always access those. I do think, though, it's better just to be here. If you're here, you're able to ask questions. Calculus is a fascinating subject. It's by far my favorite class to teach. Physics I really like teaching a lot too, but I'm not teaching that this year. But it's just next level stuff. Calculus allows you to delve into interesting questions that really have been out of our reach in the past. Calculus opens some doors, and you'll get a sense of that pretty quickly. So I'm hoping that you come to view this as a fun place to be, but it's going to be challenging. I mean, that's the whole point. You guys are remarkably intelligent people. You wouldn't be here if you weren't. I'm going to help you expand your horizons and get even smarter. I'm going to push you in this class, which means that you are going to have some questions. So it helps to attend. Okay. The Google Meet procedure that I screwed up today, here's how it'll typically go. I'll have the link hidden to the calculus class to drop into Meet, and then I'll go in first and open up a session like between classes, and then so typically like a minute or two before the start of class, you'll see that link become live and you can hit that thing. I've got a lot of things to do between classes. I've got to save my videos to YouTube, etc. So it's possible that I might occasionally be a minute or two late on that, but just be patient, okay? Office hours. The way that you will attend office hours is like this. So if you go to, if you look on the Google Classroom, really the stream, there's not much going on there. Every once in a while, I'll send out an important message, but most of the action is happening on the classwork tab. That's where you're going to want to be. Up at the top, you're going to have some information and resources that won't change. I'm going to put, for example, you guys won't be able to see this quite yet, but the instructional videos will be available in a folder there that you can just quickly link. You can quickly access and see all the videos. My office hours, when you want to attend office hours, they're between the hours of 1:15 and 3:30 on every school day. Just click on this link, and there's going to be a Google Doc that I will revise daily. This URL that drops you into the meet session for office hours will change on a daily basis, but it'll be ready to go before 1:15 every day. The reason I do it this way is so people from all my different classes can drop into a common meet session. That's the way I'm going to choose to do it. If it turns out that it's too confusing to have Algebra 2 students and Calculus students in the same office hour room, then it's possible I might set up some restricted times where Calculus gets half of that time and Algebra 2 gets half of that time or something. But I want to try it this way. So it'll just be one common Google Meet that people can drop into and out of as they need to. Does that make sense? Okay, and here's where you get the access to that. What else? I got a little get to know you activity. I'm not going to make that mandatory. I know most of you pretty well, but if you have time, in the next week or so, just fill that out. It's interesting to me to see what your responses are, but I'm not going to require it. So here's going to be our first unit, and here's the way we'll structure units. Unit 1 is going to be on limits and continuity, and there's going to be a resource available, a Google Doc that I will add to as we move throughout the unit. So right now there's not a heck of a lot there. We're just starting section 1.1, but the assigned reading, if you click on that, for example, it's just going to be day by day, what do I want you to, so for section 1.1, here's the reading I want you to do. And what does BP stand for? Do BP 99? What do you think that is? Yeah, beginning a period. So I want to have it done before we start our class period. So that'll be tomorrow. I want you guys, well, actually for you guys, it'll be the 10th. I should change that. It's going to be the 10th. Because we don't meet tomorrow, but you get the idea. There's some additional resources. I'll always have what I call the Larson AP text. That's going to be, in case you're someplace where you don't have your book, this is going to be the screenshots of the book, of your textbook. However, it's actually not your textbook. It's a newer version of your textbook that's specifically geared towards an AP class. It's very similar, but you might even want to, even if you're reading your physical copy, it might be worth just glancing through this too to see if there's anything additional there that wasn't covered. Okay, so that'll always be there under the additional resources. And then lots of times I'll also have a link to an OpenStax course. This is a free online textbook. It's very good. So it's some additional information. I don't want to just kill you with information here, but sometimes if you need some help outside of school hours, this is another really good place to go. Okay, it's got, I think it's well organized. I'm a big fan of OpenStax. The assignments. So the assigned reading, this just shows up as a little quiz. So when you do, it's due 9:10 at the beginning of the period. The assigned reading, all you'll do is you'll go into this Google form and essentially just give yourself credit. That's all it is. You either did the reading or you didn't. If you did the reading, you get credit for that. If you didn't do the reading, you don't get credit. So that's kind of up to you guys to take care of that. And then the Canvas assignments. So the first assignment is going to be due tomorrow at 1 p.m. And if you click on this, what you're going to get is a link to the Canvas, to our Pendleton Canvas courses. This will probably be the only Canvas course in which you're enrolled. So if you click on this, you'll probably just see the calculus link. When you go into Canvas, what I want you to do is, on this first one, is open the 1.1 e-ticket in Canvas. And when you click on that, I think it's all working fine, but we'll see, I guess. It's not as, those of you who are familiar with my Moodle stuff, you'll see that this is not as good. It's the same kinds of questions, but the organization is not nearly as good. You can't just freely navigate around from question to question. You have to go through them in order. You can go forwards and backwards in order, but it's a little bit cumbersome. But for now, that's all we've got. So there's going to be an e-ticket due tomorrow, and then the first assignment is not going to be due until Monday. We'll have another e-ticket when we meet again on Thursday. There will be another short e-ticket that will be due on Friday. But those are typically really short. The e-tickets are due the next day. Typically, there are 3 or 4 problems. The homeworks could be a little bit more substantial. Okay? Questions so far? I think you'll be fine with all that stuff. What else? Okay, we talked about office hours. Syllabus. I'm not going to spend a ton of time talking about the syllabus. It's pretty standard stuff. I mean, it's you know how I work. This is very similar to in the past. Here's just a couple screenshots of the syllabus. If I don't have that up on my course resources, it will be shortly. You know that because this is an honors senior class, 10% of your grade comes from practice and 90% comes from assessments. This might change a little bit, actually. I don't know if we're going to do these daily questions. It seems like that's just maybe a little bit too much. We'll probably end up just doing e-tickets and homeworks, probably 3% and 7% or something like that for the breakdown. Tests will be 90%. Math Excel does allow me to, it's a pretty good environment. You're familiar with that from last year. It allows me to do some things that you'll appreciate, like it'll allow me to give you an additional retake. Instead of just one retake, I'll give you 2 retakes on the tests. You can do those out of sequence if you want to, so you can go back and retake earlier tests. I would encourage you to do that. You know my philosophy on that. I really don't care when you learn it. I just want you to learn it. I want you to walk out of the class knowing it. I think that's it. Anything else? Oh, accessing videos. The videos, I think I showed you just a little glimpse of that. We don't have any yet, but when we start having videos, we'll talk a little more about this. There will be in the Google Classroom, under the course resources, there will be a folder with videos. You can access them that way. And I think I'm also going to put them on the playlist like I did in past years. So whichever you prefer, they'll be available both ways. Okay? Oh, and then the videos. So there will be 2 types of videos. There will be the instructional videos like today. And then I'm going to actually make recordings of the office hours whenever I get questions. I'll just start the recording when I get a question. And that way, if you want to go in and kind of scan through the office hours to see if somebody asked your question, I'll make those available as well. Questions? Sound good? Okay, so let's dive into a little calculus then. All right, so let's start off with this is kind of a representation. You know me, I really like the physics stuff. That's what my background is in. And let's talk about, just real briefly, and we're going to have to come back to this because we're not going to be equipped to answer this question yet, but within a few days we will be. So what about traveling at high speeds? If we wanted to, for example, colonize some other star systems, for example, like go to eventually, maybe if humanity sticks around long enough, maybe we'll get there. Is that something that's plausible? Okay, it's oftentimes people talk about it'd be easy if we could just exceed the speed of light, right? Speed of light's pretty fast, but it's not infinite, and it can be problematic. Okay, so it turns out, we'll go into this in a little more detail. It's those science fiction shows that we, in movies that we see where they go at, many warps or, warp speed where they're exceeding the speed of light, is probably a pipe dream. That's probably nothing that's ever going to happen. And we can talk more about why that is in this unit, this first unit, when we talk about limits. We're going to come back to this equation right here, but it has to do with the relativistic mass of any object. The relativistic mass depends on its mass at rest when it's not moving, the speed of light, which we denote by c, and the speed of the ship relative to its reference frame where it starts. And that's what we call v. And so this is the equation we're going to come back to, and we're going to invoke the concept of limits that we're going to start talking about today to prove to ourselves that interstellar travel probably is not going to be so easy to do, if it's at all possible. Okay? All right, so moving on to limits. With this group, I will say that you guys were such an advanced Algebra 2 group that actually, hopefully you remember this, and this will come back a little bit, but we did quite a bit of stuff with limits. So some of this should start to sound a little bit familiar. Well, before we jumped into the concept of a limit, we want to just remind ourselves how we use functions. If I've got some function written here, f of x is equal to the ratio of x cubed minus 1 divided by x minus 1, that's just some function that I could graph, for example. Okay? What does this mean, f of 3? Okay, good. So I'm just going to, in the math terminology would be, we're just going to evaluate f of x at 3, at x equals 3. And that's going to give us back some value, right? If we plug in 3, well, what do we get? If we plug in 3. I get 3 cubed minus 1. What's that? What's 3 cubed? 27 minus 1 divided by 3 minus 1 would give me 2, right? So what does this simplify to? 13. Good. And, I'm going to go ahead and pop up. We're going to use a lot of Desmos in here. And this, this is probably overkill, but let's take a quick look at this. If I pull up Desmos graphing calculator, where is it? There it is. And we define the function. You remember doing this stuff probably. We did a lot of this in Algebra 2. There's our function, right? And remember, if you use function notation in Desmos, that's really handy because then I'm able to evaluate those functions. Whoops, I'm able to evaluate those functions wherever I want to. So f of 3, sure enough, it equals 13. And if we want to look at the point, 3, let's do this, a, f of a, and we'll just let a equal 3. Okay, now I can choose any value I want for a, but there it is, right? Not surprisingly, it's just a point on the graph, no big deal. Okay, so it's useful for us to use functions. Functions represent things in the everyday world, and we might want to make some predictions based on some function that represents some kind of physical behavior, for example. Okay. Okay, well let's try another one. Same function. What about f of 1? If I evaluate the function at 1, what do I get? 1 cubed minus 1 over 1 minus 1. What's that simplified to? 1 over 0. I get 0 over 0. There we go. Okay, what's that mean? Okay, so it's undefined, isn't it? Right, and we talked about this in a couple of years ago. First of all, there's a big red flag here, isn't there? What do you immediately see and you say, oh, we got problems? Yeah, you can't divide by 0, right? We've only got 2 rules for real numbers. We can't divide by 0, and we can't take an even root of a negative number, right, for real numbers. So right away, we've got a red flag. That's not going to work. And then furthermore, if we have 0 over 0, you might remember, and we'll talk a lot more about this really soon. We'll review this stuff. That means it's an indeterminate form, so we don't know we have to do some more work. We don't know what's going on there. Okay, but the point is that evaluating this function is not helpful, right? We don't get an answer that this was not as straightforward and useful as the last example we did. We got 13, end of story. That was useful. We know that when we evaluate this function at 3, the answer is 13. This one, when we evaluate it at 1, it breaks. The function is not defined at 1. In fact, if we were going to write the domain of this thing down up here, we'd have to say that x is not equal to 1. And we can see that right away because we've got an x minus 1 on the bottom, and we can't divide by 0. So we have to exclude 1 from the numbers that we can evaluate this function at. It's no longer in the domain. But we might want to know what's going on there. It might be useful for us to know what is the behavior of the function around x equals 1. Even though the function doesn't exist there, it might be useful for us to know what's the pattern near x equals 1. And if we graph the function, well, we've already got this graph, right? There's the graph of x cubed minus 1 over x minus 1. Now, if I let a equal 1, or if I do f of 1 up here, well, Desmos is smart enough to know that it's undefined, but I can't even I can't even create that. Obviously, Desmos is smart enough also that it's not going to let me graph something where the function is not defined. How do I do this? Whoops, that's not what I want. Oh, here we go. Let's just go -2. So if I drag this thing along, when I get to 1, it disappears because it's undefined, and every place else it exists. That's one real weakness of using like Desmos or any other graphing utility. You can't see that there is a hole in the function at x equals 1, can you? Right? There's no, it'd be nice if Desmos had the feature, and maybe this will be in some future iteration of Desmos. It'd be nice if it would do something like draw a little open circle wherever you have a hole. It doesn't do that though. You can always test it by just evaluating the function, but we've got to be able to make predictions where those holes exist. What is the behavior of this thing though? If an ant were walking along, and we're going to talk about this a lot too. If a two-dimensional ant, this is our calculus ant, were walking along this function on my whiteboard here, what value of y would the function be, would the ant be approaching as his x value approached 1? What do you think? I mean, as he takes these steps, here's our green ant. He's walking along the function towards x equals 1. As he walks towards x equals 1, he can't step on x equals 1 because the function doesn't exist. But as he takes that last little itty-bitty ant step towards x equals 1, what y value is he approaching?
Wouldn't we be approaching infinity to the
Well, he's okay. Approaching infinity. Well, let's make these. I'm just going to play around with this a little bit. Let's make these steps a little bit smaller. Make them steps like that size. Okay. If I just animate this, look what happens. The ant walks back and forth towards x equals 1. Notice that he blinks out of existence when he steps on 1. But what's the y value that he's approaching as he nears an x value of 1?
3?
Yeah, everybody see that? It's 3, right? As we approach 1, he thinks he's going to step. He doesn't because the function doesn't exist, but that's where he thinks he's going to go. Everybody agree? Okay, that's what we call a limit. That's what a limit does for us. In calculus, a limit sounds like it's something really complicated, but it's really not. The limit of this function, the limit of f of x as x approaches 1, and you might remember this notation. And I'm going to write the function down. The limit of x cubed minus 1 over x minus 1 as x approaches 1 is 3, because that's the value that the ant is approaching. That's the whole purpose of a limit. With a limit, we know that the function is not defined at 1, but we want to know what value of the function do we approach when we get infinitely close to 1, right? Because we can get arbitrarily close. We could go to 0.99999 repeating as far as we want to, right? Or if we're approaching from the other direction, 1.000001, right? We can get really close to 1. We just can't ever actually go there because x can't equal 1. So this sounds a little hokey, but right now we're going to think about this in ant terms. The limit of a function is the value of y that the ant anticipates stepping on when he gets to a certain x value, in this case 1. Okay, now we know that he's not going to ever be able to go there, and that's a really important point. This is probably the most common misconception that people have about limits, is that, you know, the ant, you never really get to that x value in a limit. We're just talking about the value that we approach, the value of y, or the value of the function that we approach as we get arbitrarily close to that number. We never can actually get there, though, right? Does that make sense? Kind of? We'll get back to it. Give me a thumbs up if so far so good. Okay? Okay, so as we mentioned before, just a quick summary. The whole concept of a limit here is just that we get the 0 on the bottom, right? And a 0 on the top, and that causes problems. We'll spend more time looking at that. So let's look at some other graphs. Let's look at 3 kinds of graphs here. We've got f of x equals x to the 4th, or x squared minus 4 over x minus 2. That's f of x. We've got g of x equals the absolute value of x minus 2 over x minus 2. And h of x is equal to 1 divided by the quantity x minus 2 squared. Okay, what do these all have in common? What are the domains of these functions? F of x, g of x, and h of x. Remember, and quick reminder, you guys tell me what's the definition of domain?
The values of x
Good.
that are the function evaluate, and the commonality is x cannot equal 2.
Good. So the domain, though, that's the set of all possible input values of x in this case. And you look at all these functions and notice that they all have an x minus 2 on the bottom, and so x cannot equal 2 because that would give us a 0 on the bottom. So in each of these cases, all 3 of these functions have the same domain, which would just be that x cannot equal 2. Okay? If we were to graph these functions, we get different kinds of things going on. Like in the first graph, f of x, this is an example where we just get a hole in the function. And you might remember from Algebra 2 how we could predict that's a hole. We'll get back to that soon. The second function, g of x, once again, there's a place where the function's undefined. Now, this is a different kind of thing going on here, though. It's not a hole. There's actually a break in the function, right? And then finally, h of x, once again, we get x equals 2. The function's undefined, but this is still a different kind of behavior. This is a place where it's undefined and we get this vertical asymptote. Okay? So they all have different things going on. In all 3 cases, x cannot equal 2, but when we talk about the behavior near 2, we're going to get very different results for all of these functions. Okay? And we'll come back to that stuff. Let's look at this first one. So first of all, let's take this first function f of x, and let's take a couple limits. Well, what's the limit of f of x as x approaches 0? It's 2. Yeah. Why is it 2? Well, because that's the value that the ant anticipates stepping on. The ant anticipates step point 0, 2, right? Okay. So does it matter that the ant actually, could the ant step on that point? Is it in the domain of the function? He could. If the ant steps on x equals 0, he has a y value of 2. We can say that by just evaluating the function. F of 0 equals 2. That's a true story, right? The ant can step on an x value of 0, and when he does, he has a y value of 2. Okay? What about this second limit? What is the limit of f of x as x approaches 2? And you can just base it on the graph here. In fact, let me make a point here real quick. Well, we're going to talk, I want to introduce the concept of a limit, but today's discussion really is pretty simple. We're just going to find limits or evaluate limits using graphs and number tables. Later on, we'll talk about sort of the calculus way of doing this, using analysis, an algebraic approach. But for today, we just want to know what the concept of a limit is, and we want to be able to look at a graph, in this case, and based on the graph, what's the limit? The limit of f of x as x approaches 2 is what? 4. That's correct. Whoops, that's bad 4. How come? What are the coordinates of that hole? Okay. Now, in a limit, does the ant ever actually get to 2? Right? The most important part of the behavior of a limit. The limit of the function as x approaches 2 is what's happening as x approaches 2. In the limit, the ant never gets to 2. The limit just is making a prediction based on the behavior of the function. What would the place be where the ant would anticipate stepping? Well, based on the behavior of this thing, if the ant's walking along the function towards x equals 2 from the left or the right, doesn't the ant anticipate stepping there? Right? So the limit of the function is 4. That's what he thinks his y coordinate is going to be. The value of the function is the y value, right? He thinks the value of the function is going to be 4. In this first limit, as the ant walks along the function from the left or the right, when he steps on x equals 0, he anticipates stepping on the point 0, 2. And so for that reason, the limit of the function is 2. There's a key difference here, and that is that in the first case, the ant actually can step on 0, and in the second case, he cannot step on 2. But we don't care. As far as the limit's concerned, that's irrelevant. As far as the limit's concerned, we just want to know where does he anticipate stepping. Okay, and in the first case, he anticipates stepping on 2. In the second case, he anticipates stepping on 4. Okay? Questions? So far, so good. Okay? Once again, in the limit, he never actually gets there, though. Okay, what about one like this? How could we do a problem like this? Like we've got some bizarre function. We could graph this thing, but let's do it without graphing it. If we've got this function f of h equals... Whoops. F of h equals 1 plus 6h to the 1 over h power. And we want to make a prediction here. Well, what's the limit of this thing as h approaches 0? What's the domain of this function? Any ideas? And we're going to practice this stuff. Got 1 plus 6h to the power of 1 over h. Yeah, x can't equal 0 because, look, we've got an expression here in our exponent where an h is on the bottom, and you can never have a 0 on the bottom, right? So h cannot equal 0 is our domain. Okay? So we can't evaluate the function there, but we might want to know what the behavior of the function is as h approaches 0. Okay? Well, we've already looked into some examples where we use a graph, and that's fine, and we'll come back to some more of those. We don't have a graph this time. So what we could do instead is we could maybe even do something a little bit different. We could use like a data table, right? What if we were to make a table of values, and we're going to have, I'll do a horizontal table where we've got values of h, and we've got values of f of h. And we're trying to get to the value of h equals 0 where the function is undefined. Right? So it doesn't exist there. But if the ant were to walk his x values in towards 0 from the left or the right, we could do something like maybe negative 0.1, negative 0.01, negative point, whoops, negative 0.001, and so on. And from values greater than 0, we could work our way backwards from positive 0.1 to positive 0.01 to positive 0.001. Why might that be useful? Let's see what happens. What if we make a table? Let's go back to Desmos. Now I got to remember how to do this in Desmos. You might have to help me out. So let's define a function here. We'll call it f of x. Okay, so it gives us a graph. gives us a graph, and then we could use that, but let's not cheat and use the graph. Not this cheating. Let's make a table out of this. So I could make the table manually. I could just plug in some values. I could try, for example, f of negative 0.1, and that's going to give me some value here that I get that I could plug into my table if I want to. So what do we get here? 9536.7. And then I could get a little bit closer, and you can already see how this is going to work. I could add another 0 there. And look what that does. That's going to get me towards some other value. Okay? And I could add, it gives me another value. I could add another 0, and I get another value, and I could add another 0, so I'm getting closer and closer and closer and closer and closer. What do you notice about the numbers? As I push closer and closer and closer to 0, what do you notice about the outputs of this function? They change less and less and less, and I end up getting closer to some specific value. I should see the same thing from the right. If I try positive values, I might start off quite a ways away, but as I get closer and closer and closer, I'm converging on some specific value, right? The ant's walking towards the same number from both sides. And so one way I can do that is with a table. If I just fill in these blanks, whatever number I seem to be approaching from both sides as I get very, very close. And how close is close enough? Well, it depends. How many decimal places do you want? If I want to get the same number to, let's say, 2 decimal places, well, as soon as I start getting the same number from the left and the right, as I approach 0 from negative and positive numbers, then I've gone far enough, right? As soon as this number isn't changing out to 2 decimal places from the left and the right, I've got my answer, okay? In this case, to 2 decimal places, it ends up being 403.43, I guess, if you fill that table in. There is a way on Desmos, and let's just take a quick look at this. If I go, if I don't remember how to do this right now, we'll do it next time. But I think, let's see here. If I go add a table, and, okay, I'm going to make this there we go. So you remember doing this in Algebra 2. When I want to make a table of values, I have to have like the subscript 1 on there to tell that indicates that these are specific values of variables. So I could do something like then. I could go negative 0.1, and it'll give me the corresponding y value, right? And then I could go negative 0.01, and it gives me another y value. Well, if I want to, keep getting smaller and smaller and smaller, I can just follow a trend here. I mean, I could keep on typing in values manually, or I could do something like this. I could go like negative 0.0000000009, and then I'm just going to copy that. And make it, oops, darn it, make it an 8. And then I think I can just keep stretching that. Oh, how come it's not doing it? Oh, I thought it would do that. I thought it would just fill in the trend if I did that, but maybe I'm wrong. I don't know, maybe I have too many zeros. Oh, I don't know. I can understand why it's doing that. I thought it would give me values that it would just kind of naturally fill in that list, but I guess not. You don't really have to have that many values, though. Really, all you'd have to do, and I know I'm kind of rambling here a little bit, but if I were doing this problem, an easy way to do it would just be to add as many zeros as you need. Like I could go negative 0.01, and then I could do positive 0.01. Well, those aren't close enough, so let's add some more zeros. Let's add 3 more zeros. Now we're getting there, aren't we? So let's add a few more. Look what happens. Okay, now we've gotten close enough so that when the ant approaches 0 from the left and the right, he's ending up at 403.43 from both sides. So there's no reason to add more zeros because out to 2 decimal places, I know what the answer is. It's that. Does that make sense? Okay, once again, in Desmos, when you want to use the tables in Desmos, remember, you're going to enter the function, and then you have to have an x1 and an f of x sub 1. And the place you get those tables is you go up to add item, and you add a table. Okay, and then you can calculate output values based on the function you define. Okay, so just a little shortcut. Let me ask you this though, does this seem a little hokey? Doesn't this seem kind of non-mathematical in a way? We're having to use graphs and make these tables. Wouldn't you agree that there's something not very satisfying about that? Because what if I wanted to, on this last example, what if I wanted to have an answer that was out to 1,000,000 decimal places or 1,000,000,000 decimal places? I don't know about you, but I don't have time in my life to sit there and add enough zeros to get the right answer out to 1,000,000 decimal places, right? So there's got to be a better way, and there is, but we're just not talking about it today. Today we're just looking at tables and graphs. I promise you, we're going to find a way to get exact answers that aren't just decimal answers too. Okay, questions so far? Okay, making sense? Let's start to talk about, be a little bit more precise about our definition of a limit. Oh, and we're out of here in 2 minutes, aren't we? So you know what? I'm going to skip that slide. Here's another representation of tables. Just wanted to make sure this makes sense to you. You know, I would encourage you to use Desmos for these tables in real life if you want. If you don't want to, you don't have to. But if I wanted to evaluate this limit that we talked about earlier using a table, we're trying to evaluate as we approach 1. Well, we know 1's not in the domain, but I could just pick values that are less than 1, but increasingly close to 1, or greater than 1, but increasingly close to 1. So we'd say in math, x is either approaching 1 from the left, from negative values, or x is approaching 1 from the right, from positive values bigger than 1. In either case, we're approaching a value of 3, it looks like, doesn't it? Right? So that's our limit. Okay, I'm going to call her quits there.